Hello everybody, I'm Santi Adavani and I'm going to speak on behalf of myself and my colleague Vinay Rao. And the topic of my talk is from Genomics to NLP, one algorithm to rule them all. So for those of you who haven't met it, this a quick background. I got my PhD from UPenn, specializing in high-performance computing and computational sciences. And after that, I worked at Intel for 8 years as a senior product manager. And now I'm the co-founder and CTO at RocketML. RocketML is a machine learning platform for large data sets when the current tools do not scale or outright fail to work. This is the outline of my talk. I'll quickly do an introduction of what I'm going to say. And the second one is making sense of SVD, the algorithm that I want to talk about. And one algorithm to rule them all, why do I strongly believe that's the case? And talk about large scale, scale out SVD. Whether you are a data scientist working on genomics, that is, you're trying to cluster genes based on how they respond, or you're working in neuroscience trying to understand different nerve cells and their behavior, or in natural language processing, trying to build semantic search engines, or in finance, trying to predict stock prices, or in cybersecurity to identify anomalies, or in healthcare. One problem as data scientists that we need to keep up to is the number of new algorithms and the number of new tools that are published on a very regular basis. So what if I told there is one algorithm that's been around for more than 2 centuries, and there are 4 million plus publications which have actually shown to work on all these applications? So if you're venturing into a new area where you have to try out various new things or get up to speed, or when you're working on a new tool or new algorithm, I would say singular value decomposition is something that you can always benchmark with, or something that you can always go back to and see, how can I actually use it? It's not specific to supervised learning or unsupervised learning or any of the specific learning techniques, but it can be applied across quite a lot of problems. And it's the versatility of this problem that makes it very interesting. So this is the formal definition of singular value decomposition, in short for SVD. That's what I would call it from now on. And it's a matrix factorization technique where you split a matrix into 3 parts: U, sigma, and V transpose, where U and V are orthonormal. That is, if you take 2 columns of U and do a dot product, you would get 0. And if you take any 2 columns of V and do a dot product, you'd get 0. And sigma is a diagonal matrix. So intuitively, what it is doing is, if M is a 2 by 2 matrix, and you apply that matrix to a vector, the matrix is doing 2 things. 1, it stretches the vector, and 2, it rotates the vector. What the decomposition is doing is it is breaking that into 3 parts. The first part is taking care of just the rotation, and that gives you the bottommost circle where you're rotating the vectors. And sigma, because of its diagonal nature, it helps in stretching the vector. And U, again, basically rotates the vector. So it's this decomposition, U, sigma, and V transpose, that can be applied in various different areas. So either you could use it as a preconditioner, or you could use it in supervised or unsupervised learning. So it's a combination of either V or sigma or U or multiple combination of these 3 that you would make use of in various different applications. And I'll actually go over a few in this talk. And The others in the same family, you'll probably run into a lot of these names or these algorithms in your data science journey. One of the most popular ones is principal component analysis, in short PCA, eigenvalue decomposition, latent semantic indexing. This is the same technique, but used for building semantic search engines in natural language processing. And latent semantic analysis. Basically, you use the same technique, but you can do topic modeling using LSA. So when you run into all these different names, they all belong to the same family. Making sense of SVD. So one of the most popular applications of doing SVD is dimensionality reduction. So I'll walk over one example of dimensionality reduction and explain how you can actually use these three components to, for this application. So my matrix is an image. This is an image of Mount Hood taken from Pitock Mansion from Portland. And the image is of size 450 by 400 pixels. So my matrix has a size of 450 by 400, where each entry corresponds to the pixel intensity. So it goes from 0 to 255. So when I do a matrix decomposition, I get these three vectors, three matrices. So U, sigma, and V transpose. So U is of size 450 by 400, sigma is 400 by 400, and the V is 400 by 400. So when people talk about dimensionality reduction, what we essentially are saying is we want to kind of reconstruct my data or reconstruct my matrix by using just few components of all these three matrices from my decomposition. That is, I just take the first n columns of U, just the first n values in sigma, and the first n values of V. So by reconstructing the matrix, that is by just dropping a few columns and a few sigma and few V, we can reconstruct the whole matrix. So here one thing that to remember is the values of sigma or the diagonal matrix is in the reducing order. That is, the first entry there has the maximum value and the last one would have the minimum value. So the problem that typically we run into is where do you put off the cutoff? Where do you actually cut it off? How much n do you use between 0 to 400? Should I use 1? Should I use 2? Or should I use everything? So one way to answer that question is by actually looking at the singular values. So for this specific problem, when you plot the singular values for this matrix, you'd see that the matrix, the singular values are actually decaying. These are the diagonal entries in my sigma. And a rule of thumb for you is whenever you see a quick decay in singular values, there is scope for dimensionality reduction. That is, you can reduce the dimension without a lot of fear of losing information. If it is flat, I would stay away from dimensionality reduction and I would actually analyze my problem further. In a lot of cases, there are thumb rules saying, hey, I use the first 100, I use the first 400, but I don't think they're very sound in terms of coming up with a number without looking at the problem. So where do you put the cutoff? On the right-hand side, what I'm showing you is the cumulative sum, which is in the denominator and actually adding up more singular values on the right. So on the rightmost hand side, what I have is the sum of all singular values divided by all singular values. That is, I'm using the entire U, entire sigma, and entire V. So I'll be able to reconstruct the whole thing, the whole matrix. But if I want just the 90%, right, I'm okay dropping off 10% of my information. All I need to use is the first 150. I don't need to go all the way to the 400 that I got from my decomposition. If I'm okay leaving out 20%, not much, 20%, that is I take 80% of the matrix, all I need to use is the first 100 singular values. 50, even further down. So when I drop these, how does the reconstruction actually look like? Can I get back my image? And this is how the image that I took actually looks when I start adding more and more singular values. So the first one is when I have n is equal to 2. That is, I just take the first two columns of U, first two of sigma, and first of two of V. And you can't really see anything, but kind of start to get to feel that there is something happening in the horizon. Same thing with 3. But once I start increasing to 20, right? So in this case, I've used 20 columns and 20 singular values. The total matrix size summation of all these is 17,020. That means it's only 10% of the overall entries in A. But I can start reconstructing my data. And when I go to 100, which is 85,100, which is 47% of my matrix, I cannot really distinguish between my original data, which is the image, and the data that I reconstructed using over the first 100 values. If I go further, which is 200, you can't really say the difference, but it's 94% of the data. That is, you only get 6% reduction in your overall data size. So this is an application in signal processing, and where you want to actually send the data across network, where you don't really care so much about losing a lot of information. So when you want to send data across network, if you go to 100 singular values, you're actually reducing 50% in bandwidth. So there's a direct application of SVD in signal processing where you can reduce the dimension. You're actually reducing the number of packets that you want to send across the network, but at the same time, you're not losing a lot of information that you're sending out. So the idea is basically how do you use SVD in different cases. So the key points that I want you to take away from the example I gave was, if eigenvalues are decaying fast, then there is scope for reduction. So what you're doing in turn here is you're dropping the components. That means you're dropping the components that are noisy or that do not actually contribute a lot to your data. And when you do that, in return, you're actually identifying components that contribute to the data the most. By doing these two, you're actually reducing the dimension without losing a lot of information. And that's some of the key takeaways from understanding how to use SVD. So why do we say one algorithm to rule them all? So I'll go over 3 applications. So one is in supervised learning, unsupervised learning, and I'll introduce a new term, a new problem called inverse problems. So these are the problems that are very popular in the scientific research area. So when you do supervised learning, at least now the traditional wisdom is we'll use deep learning. And we love deep learning at RocketML, and it works great. But one problem we run into is when you're given a data set. That is, you have M samples and N features and M labels, and that's a pretty large data set that you may end up with. The idea is, in deep learning, you throw all these N features into your network, and you don't really worry about what the network is doing to your features. So the feature engineering is taken care, and it works great for a lot of problems. But what if you want to kind of understand how you're actually engineering features, while not losing the advantages of deep learning? So one way to do that is transform your data by using the components that you get from SVD and reduce the dimension. While you're reducing the dimension, you're actually throwing away a lot of components that are noisy. From our previous example, we are actually throwing away components that are very noisy. So the way to deal with supervised learning problems, and this works very well along with the other techniques, is you start off with the decomposition. That is, you say A is equal to U sigma V transpose, and you recompute your input matrix. So you say A prime, which is a new matrix that you're going to create, is A times V. And instead of using all n features, you're actually reducing the overall problem size to small n. So when you do that, it's not just you're reducing the problem size, which is great because with a smaller problem size, you can actually run through quite a few algorithms faster. But in essence, you have also dropped a lot of components that may not actually help in doing your predictions. So we worked on quite a few problems where before venturing into deep nets, we would actually just take A and do an SVD, cut off some singular values, and make a smaller matrix, and we would get really good results. Obviously not as great as deep learning, which gives human-level accuracy with a lot of data, but you would actually get very close to what you would expect with, for a good problem to solve. So this is how you could actually use SVD in the context of supervised learning. And for unsupervised learning is the same idea where you don't have labels anymore. You just have a data set with m samples and n features. And you want to use SVD for doing, say, clustering or nearest neighbors or anomaly detection. So in a few minutes, I'll actually talk about anomaly detection. And so one thing, well, you see this equation here, A is equal to U sigma V transpose, you think that, hey, I need my entire A or my entire data set in a single shot. And in most of the real life applications, you will not have your entire data in a single shot. You would have streaming data. The data is coming in at different time points. And in order to accomplish SVD on streaming data, there is an algorithm called frequent directions. And I'll walk over step by step on how you can actually deal with SVD along with streaming data. And the application here I'm going to follow up with is in cybersecurity. So we have a matrix A, which is of size m by n. And m is the number of rows, and n is the number of features. And the problem here is I don't have my entire A in a single shot. I'm getting one row at a time from different inputs. So assuming I just want to go for the n first singular components, n components of U and n of sigma and n of V, I start off with a smaller matrix, which is 2n by n. So at the minimum, I need 2n rows or 2n features. So using that B, a smaller matrix B, I compute my U sigma V transpose. So I basically do a smaller matrix decomposition, and I actually compute U sigma V transpose. So once I get these three components, I drop off all my last n rows. So I make the last n rows zeros, and I use my first n rows and normalize them with respect to a value as a function of the singular values. And now I replace all my remaining n rows from the next n rows that I get from my matrix. And this makes it a new matrix B, but the values have changed. The values here have n rows coming from my data set, which is A, and my first n rows corresponding to the singular values I computed using my original matrix. So I keep repeating this. That is, I basically drop off my last n rows and add new n rows based on the new data I get. And this is how I can actually keep updating my singular components by not worrying about whether I have data or not. And this can be applied in recommendation engines, can be applied in cybersecurity and various other applications where you don't have all the data in a single shot. So in cybersecurity, example I have is an anomaly detection. So I have a website, and all I care about is images of fighter jets. And if someone uploads anything else, say in this case, a camera, I want to flag it as an anomaly, right? So here, the application is, the first step is I need to create a matrix. And in this case, my matrix is a sequence of images. So my rows are images where I reshape and resize everything to have the same feature size. And then I basically decompose the matrix into U, sigma, V transpose. So once I do that, for any new image or any new data point that I get, I basically compute a score, which is a single value. And that score I basically compute as this equation. And this is a recent paper in 2018 that talks about how to use SVD for anomaly detection. And for a new image Y, I compute anomaly score, which is basically I minus V transpose Y. The intuition is finding the closest point to Y when you do it form it as a linear combination of vectors in V. That is, you're trying to see if any of my original or normal images are close to this, but using my singular values, because you're dropping a lot of noise that can be present in your original data set. So when I take 50 images, this is one image for the normal case, and I compute the anomaly score, I see that my score is around 5. And this is the 10th image out of 50 normal images I took and computed the score. If I take another fighter jet image and compute the anomaly score, and it is also very small, which is basically, this is the 30th image, and the score is close to 5. So now I start throwing in images that are not my sense of normal, and they have a very high score. They have a very different score, which is very close to 20. And if I use something totally out of whack, the anomaly score is really high. So here we are using the decomposition to actually figure out anomalies on the fly and eliminate them from your stream of data. And you can actually fit this whole component into your SVD streaming data, which is here. So the previous example we talked about was you take your data, you basically compute your SVD on smaller data set and bring it back. By having this component, the anomaly detection component, which can be used for threat detection during network data, or in security, or actually even in video surveillance, basically you can put in this anomaly detection piece, and you can quickly identify whether it's an anomaly or not and take appropriate action. So this is an application of SVD for anomaly detection, which goes into various different areas. So I'll introduce to inverse problems. So at RocketML, we think like, what next? Like, what are the next challenging problems that we could come across? And one problem or one set of problems that we imagine or we see, at least in the literature in the scientific community, is inverse problems. So this was a problem I worked on back in my grad school. So we were trying to build an AI to assist cardiologists. So the problem here is a quick 101 cardiology. So this is basically a node on the top left corner of heart called sinoatrial node, which is a natural pacemaker, which results in a pulse that propagates through the entire heart. And that pulse is what gives rise to the heartbeat. And that's what you're measuring in ECG. Thus, that electric pulse propagation is what we measure in ECG. So cardiologists at Penn, when they look at the ECG, they can tell that there is a problem. There is something going on in your ECG, and there is a problem. But what they wanted us to look at was, can you guys help us find where the problem is in the heart tissue, given a lot of ECG data? Because we can tell that there is a problem, but can you help us tell where the problem is? That means we need to identify where the problem is within this heart tissue. So this, we formulated it as an inverse problem, right? So just to show, so we can simulate the entire heart behavior to some approximation using a partial differential equation. You can represent how the pulse propagates using a reaction diffusion equation. So a forward problem is solving this equation, a three-dimensional equation. Given A, we can find U. The inverse problem is given U, which is ECG, we want to solve for A. So A here is a spatial property that represents the heart tissue properties. So if A is a function that it is not normal, you can actually go and say, hey, this is your three-dimensional model, and this is where the problem is. So solving this forward problem and solving this inverse problem is computationally very expensive. You cannot throw a lot of GPUs at it, or you cannot say, I'll use a variation of SGD. That won't cut it. This is an example of a healthy tissue on how it actually propagates electric pulses. So it starts off, I'm just showing you the lower part of the heart. This is a real heart geometry. And the pulse propagates, it starts, and it is pretty smooth, and how it actually propagates around the heart tissue. But if it is an ischemic tissue or a tissue that has problems, it's all over the place. So you could see it's like beating on the left, beating on the right, and it would actually result in a cardiac arrest. And all this because of some nudge or some tissue actually going out of normal in this entire heart tissue. So I'm not going to talk about how we solve it using SVD, but the one key takeaway I'm going to talk about is, so solving this involves solving this forward equation thousands of times. And solving it once would take a couple of hours on large-scale compute, on the Pittsburgh Supercomputing Center at the time we were working on. And if you use out-of-box solvers, gradient descents or SGDs, it would take thousands of iterations, which would be a year almost on state-of-the-art supercomputers to solve one data set problem. So in this case, you have to understand the structure of the problem. Like, what does these equations actually mean? And how can we take advantage of the structure of this problem and design very specific solvers that address this problem? So in this case, we used SVD to build preconditioners, that is matrix inversion techniques to make the solves very fast by using regular compute. So we brought down thousands of iterations to around 10 iterations, which could actually make it solve in a couple of days and not months and months and years. So that's the last application we'll talk about for SVD. And I think since we are in a big data conference, I want to throw some numbers on how we can do scale-out SVD. Like if you have really large data sets, can you compare to SVD? Like what does it take? So what we noticed is a lot of current tools, they work well, but they do not scale well. That is, as you throw more compute at it, we cannot actually see the total amount of time, runtime, wall clock time actually reducing. And these are some results that we have that we built in RocketML because of the relative importance of this technique in various applications. And this is a 14 million by 1 million data set. And the results I'm showing you are for computing 100 singular values and the corresponding vectors. And on Amazon Web Services, by increasing the number of nodes and the compute, we could actually do SVD in a pretty scalable fashion. The other data set that we went to is like, what if we use much bigger data sets where the current tools do not even cut it, they just crash on you? So we went all the way till 1 billion samples and 1 million features and constantly started increasing the amount of data we can throw at it. So on 1,000 codes, we went all the way till 1 billion by million samples. And we were able to actually compute SVD for 100 singular values in around 15 minutes. So in essence, we do not actually believe it's one algorithm to rule them all. There is nothing like that. But as data scientists, I think we need to have a lot of tools at our disposal, and some tools can be applied and used across a lot of different areas. And we think SVD is one of them that can actually make you happy across solving multiple problems. So with that, thank you, and I'll take questions.